So hello everyone, welcome to our Setup Tech Talk series. So for our talk today, we are having Dr. Pooyan Jamshidi, who's going to talk about Causal AI with application in computer system. I hand it over to you, Pooyan.
Thanks for the invitation. I'm so happy to talk about the research which one of my senior student, Shahriar Iqbal, is doing. This talk is about understanding and explaining the root cause of performance faults or performance failure with Causal AI. I will elaborate on all these technical terminologies, but this is continuation of a bit of my own research back when I was a postdoc at Carnegie Mellon University, and my student took over and now is doing his own PhD on this topic. So for those who don't know, I did my PhD in Ireland at DCU on autonomous systems, and after that I did 2 years of postdoc at Imperial College in London, and then moved to the US. Now I'm a faculty member at the University of South Carolina. Just a quick advertisement. This year, I'm co-chairing SIMS 23. And the second round of submission is coming up soon for those who are interested in topics like self-adaptive systems, uncertainty, control theory, AI and ML, and requirement engineering, and as well as programming languages in the context of self-adaptive systems. I would be happy if we receive submission from you guys. So I start off with motivating the work. As many of you know, we use ML-powered applications these days for doing many prediction tasks. For example, predicting the amount of calorie in the food that we eat. And many of these applications are actually powered by deep neural networks. As you know, deep neural network consume a lot of energy, but there always be a trade-off space where we can find the sweet spot between the accuracy that we want to get and the amount of energy that these applications consume. And this talk is mainly about how to optimally make that trade-off better. So in general, the goal of this research is to enable developers and users to find the right quality trade-off that they want to have for their own applications. And today, many popular systems, modern applications are highly configurable. For example, Apache Hadoop, which cover many big data systems these days, to robotics, as well as ML systems are highly configurable. Let me elaborate what do I mean by configurable systems by going into detail of Apache Hadoop configuration space. Here you see several different configuration options. These are for Apache Hadoop. You see the number of threads that you can set, currently 64. As you know, you can change this, and as a result, you may get a different performance. We have the amount of cache that is assigned for this machine, for this Hadoop instance, as well as some other options that you found here. They have different semantics. Obviously, they might have, changing them might have different performance consequences. And there are many of them, even for Apache Hadoop. This number of options that you see is tiny amount of the whole configuration space of the system. Not only that, but the number of configuration options for this type of systems increases over time. For example, for Hadoop, the number of options just from 2006 to 2014 has been increasing from 20 to over 180. And you know that as a result of this, the space of configurations is exponentially increasing. This is not only constraint for big data system, but many type of engines, systems. Here you see Apache Web Server, storage, MySQL, all of these highly configurable systems, the number of options has been increasing over time. You may ask, who cares about these options? Why should I care, and why these might be important? Here in this few lines of code in C, you see if these options, this is one single options, is enabled, either one line of code get executed or several lines of code get executed. As a result, even this one option would change the landscape between the execution time that this application is running and the amount of energy that it consumes. So there is a trade-off for many systems as a result. Let's now look at a couple of case studies in detail to contextualize the work and the research direction. And please ask your questions throughout the talk. I'm happy to answer at any time, and especially during these transitions, that would be good to ask your questions. The first case study is about social sensor. This is a big data systems when we looked at back when I was a postdoc at Imperial College. This is a big data system, again, has a crawler that searches the internet for example, the tweets that it crawls from the internet. And it stores these tweets, this content into another engine, Apache Cassandra in this case, and it has orchestrator, which was powered by a Storm, Apache Storm, again, yet another engine, and pushes the content into content analysis, which is powered by Apache Solr, and it provides the UI for search and as well as hooks for integrating with other applications, external applications. So you see for this system, this is the whole system architecture. We had the company that was developing this system at a specific requirement, and they wanted to increase the number of users orders of magnitude higher, essentially. But they knew that they were not able to get their adequate performance. So the easy answer for maybe addressing this challenge of basically satisfying the SLA of the system is the easy analysis based on some queue network theory that we done. We realized that we needed to speed up the crawling to 10x. Also, we needed to make this orchestrator real time. So one solution was to increase the amount of resources, acquiring better or more virtual machine from cloud, but that comes with a cost. We thought maybe we can get a different performance, hopefully better performance, by changing the configuration of the system. And our key reason was that in the system architecture, you saw 3 different engines, Apache Cassandra, Storm, and Solr. Each of these are highly configurable. So the total number of configuration for these systems is actually huge, to over 300 in the list, if you only assume that these are binary options. And you know that this number of configurations are more than the number of atoms in the universe. So finding the best configuration is challenging and is a very difficult problem. We measured several hundred to even 1,000 configuration of these engines. These are data from Apache Cassandra. Each dot, each blue dot represent one configuration. When we change it, some of these options. And you see that each configuration has different throughput, which is depicted at the x-axis, and has different write latency. We know that a better configuration should have higher throughput and lower write latency. So the green dots represent the default configuration. This shows that default configuration is not ideal. It's actually bad in terms of performance. This best configuration is located at the lower right-hand side of this plot. You see, this is the configuration that give rise to the highest throughput, the number of operations per second, nearly 1,300. Also, it gives rise to the lowest average write latency for Cassandra. And in the whole, even within these samples that we took, we already see that we can improve performance several order of magnitude. And for example, the best configuration within these few hundred configurations is noticeably faster than the median of these configurations that we measured. Also, performance behavior of the system would change. For example, if we have a specific environment, if we have a cluster, again, this is data from Cassandra. If you have a cluster of Cassandra instances, and if we change this cluster, or if we change the workload, these are the data when we change the workload, actually, the performance behavior of the system would change. You see that the left-hand side is one environment. It is multimodal. Actually, it has one prominent mode on the left-hand side, but the environment on the right-hand side has bimodal behavior. But there are also similarities in terms of the behavior of the underlying performance function that the system has. Is there any question so far before moving to the second case study?
I think due to GDPR, we have the question at the end of your talk. So we don't have to ask for people's permission. So you're going to record the video.
Sounds good. So this second case study is a robotic systems. This is Cobot, which is a robot at CMU. You see that the Cobot is moving in a corridor which has a light surrounding it. It moves to the building, part of the building which might have less light. So you see that you know already that robots for performing any mission, for moving to unknown environment, require to localize that environment. And this localization is an algorithm, which is, again, configurable. Part of the localization, when it is done during this environment, where it has natural light, might require a different configuration than when the robot is moving to a darker space. Here we measured, again, several thousand configurations of Cobot. We only changed two options, which were part of this localization algorithm, number of particles and the number of refinements. The x-axis shows the localization error. Obviously, we wanted to get a lower localization error. On the y-axis, we see CPU utilization, which is approximation of energy consumption. And the Pareto front of the configuration are located at the lower lower left part of this plot. You see this green configuration of Pareto front, meaning that these are equally good with respect to localization error and energy consumption. And obviously, we have so many suboptimal configuration that these are not providing the adequate performance. And typically, we have a sweet spot. We might have a energy constraint. We might have a safety constraint. As a result, we in some environment, we want to have a very low error, localization error, but in some other environment, we might have a more relaxed localization error. So in this experiment, here is a bit of more detailed result. We wanted to understand whether we can learn from one environment and transfer that learning into a new environment. In particular, for the robotic system, we know that we have simulator, so we can do this measurement in simulator. And if we can build a model, reliable model, we can transfer that into a real physical robot and transfer this learning, so we don't need to pay the same cost in more expensive environment. So this is the source which are given already, and the target which we wanted to predict. And we compared when we build a model without transfer learning. This is the result. As you see, the model doesn't do a good job because it doesn't capture the change of error when we build that model based on 4 measurements in the target robot. So you see that the prediction are quite accurate only around the points which we sampled, but otherwise is a flat model which doesn't provide any good prediction. This is the model that we built when we did transfer learn. Mainly we took and we reused 18 samples from the source, as well as 4 samples from the target. So in terms of cost, we did the same. We used only these 4 samples, as well as the already given samples in the source. And you see that the model started to do much better prediction. So at least it captured the change of Z. In this case, C is the energy consumption of the robot when the number of particles and the number of refinement is changing. And for those who are interested to know more detail about this work, can look up this paper where we published at SIEMS 2017 back then. And here are more detailed results of 6 different environments, where some of these environments are more similar to the target. For example, S1 to S3 are more similar to the target than S4 to S6. And the results also show that when the similarity between environments are higher, as a result, the model that we built based on this transfer learning works better, at least provide much lower accuracy, much lower error comparing with no transfer learning. And we face negative transfer in environment where the similarity between source and target are not good enough. Is the same result from different angles in terms of CPU utilization. This is the model that we built, and the plot shows the prediction error. So overall, the key question that we have asked, wanted to develop a theory to explain when transfer learning works, how source and target are related, what characteristics of the environment is preserved, and how we can transfer transfer knowledge between the environment. And those who are interested to know more detail, this is an ASC paper that we published back then. This is a paper where essentially for the experiment, we spent over 6 months for collecting the experimental data and basically doing many analyses to build up this theory of transfer learning for configurable systems. And Mohammad Ali Javidian, one of my postdocs in the lab, later wrote a paper on doing or extending the analysis by causality, and found out that many of those findings that we did based on statistical analysis are also interesting, that some of those were confirmed based on Causal AI too, but there were some contradictions as well, where we noticed with Causal AI, we can capture, for example, confounder, and we can explain better why some behavior has been observed based on the causal analysis that we could do. But we couldn't observe the same result with the statistical analysis before. So if there is no question so far, I can move on to the next part, going a little bit more detail about the current research that we do by using Causal AI for building models that help us to debug the system, to optimize system performance, and provide better insight about performance behavior of system. And I have to mention that we are not the first. Obviously, there were so many previous work that showed Causal AI are important and can help out several systems tasks, which was difficult to do before. And our work is essentially on the same line, but mainly on performance of the system. In general, as I mentioned, one of the functionality of this framework that Shahryar developed is finding misconfiguration. Misconfiguration essentially are those configurations that result in a bad performance behavior. For example, affecting throughput, energy consumption, or latency. Essentially, in this situation, the system may not crash, but it provides a degraded performance, which doesn't satisfy the service level agreement for the system. This is an example where ML system person wanted to deploy ML system in a different hardware. Previously, he was deploying and using the system on TX1, which is a small device developed by NVIDIA, and wanted to transfer that to a TX2, which is a better hardware, have a different microarchitecture. And the expectation that this person has was to get a better performance. And it is obvious because TX2 has more resources, both in terms of the computation power and memory, etc. So especially for ML, it should provide a better performance, but it was not the case. Actually, when he transferred and deployed the system, he was getting half the speed of so essentially system became slower. And this was counterintuitive. And after several discussion in the track, we noticed that the solution was actually related to misconfiguration. The configuration in the TX2 was set incorrectly, at least for some of the options, which was not that relevant. For example, clock and fan speed and power mode was set incorrectly. And it took a few days for resolving this even simple issue. For some of the issue, we noticed several months took until the issue was addressed. And the question was that how we can resolve these issues faster. Let me set the context a little bit quickly to give you a chance to understand what I'm talking about. Here, imagine a compiler such as LLVM, GCC. As you know, compiler have different options. For example, you can set to remove the dead code in the code that you want to compile, as well as some other optimizations such as loop unrolling or function inlining. Each of these options provide an opportunity for this code to maybe run faster. So imagine a program that is compiled by setting function inlining enabled. And we compile the code and deploy it on piece of hardware. And we can measure compile time, execution time, energy consumption of this program, which is running on this hardware. And imagine now, by changing this configuration, you expect that these performance metric would be different because this is intuitive. When we remove the dead code, maybe the compile time is much faster now. It doesn't need to compile the code, which is not getting executed on the hardware. So it has changing options, changing configuration for the compiler affect these performance metrics. Typically, this is done this way. Once this observational data is collected, a black box model is built, which looks like a regression model. You see one example of this on the right-hand side, where a model was built to predict the throughput of the system. And these variables on the right-hand side are the configuration options or the interactions between these options. And these regression models obviously have their own downside. Typically, they might capture incorrect interactions. So as a result, the predictions are off, are unstable, might be incorrect, and unreliable when you use that model in different environments. Let me give you an example. In this case, we changed the cache misses. So the x-axis is the cache misses and the y-axis is the throughput. This data shows that if you increase the cache misses, the throughput would be increased, which is counterintuitive. We typically don't like cache misses. We would like to have a lower cache misses or higher cache hits. And this data, at least any model that we build based on this data, provide incorrect prediction for throughput of the system. So showing increasing cache misses increases throughput, which is incorrect. We somehow, this was one example that we noticed in the data. But when we dig further and when we separated the data based on the cache policy, here we separated the data based on 4 different cache policies that was set during the measurement automatically by the hardware itself, we notice, oh, now makes sense, because under each cache policy, so cache policy, you can think about it as a confounder. Now the trend is correct, because increasing cache misses would result in a decrease of throughput. So essentially, this cache policy where you see in this model is a confounder. After capturing this confounder, we can explain why the correlation between cache misses and throughput turn out to be that way, because essentially this cache policy is a common cause of these two variables in the system. And we noticed that these causal model, as a result, would provide a more reliable, more useful, and more transferable model for performance prediction. This is, for example, a partial model that we learned in two different environments, two different hardware, one Jetson TX2 and one Jetson Xavier. And you see that the model is stable across environments. There are some few differences, but essentially these differences are minor. And we believe that these models transfer better across environments. And based on these insights, we essentially develop a framework that enabled the end user to do any performance debugging or performance optimization. And the overall framework has multiple steps. The first step is to specify performance query. Here you see a few examples of such queries. For example, when somebody noticed a performance fault and wanted to understand what caused this performance fault. So after specifying these performance queries, performance data is measured. Once we have some data, we can build a causal model. Once we have a causal model, we can formulate causal queries. Here, for example, you see a causal query on the right-hand side. What is the probability of getting a higher than 40 per second throughput when we intervene on buffer size and when we set it to 6K? Here you see also do calculus used in this performance query. I'm not going to go into detail, but for those who wants to know more about Causal AI, can look at Judy Appel's books explaining do calculus. Essentially, here mean that we want to intervene on buffer size. If we get this query translated and estimated the causal effect of the options, we can estimate these queries and answer these queries in a probabilistic way. And by collecting more data, obviously we can improve the causal model, and the estimation of this query would be improved. Essentially, these estimations are used for performance debugging of the systems and so on. So I would skip this part because of the time. But essentially, you can find more information. These are part of the data collection that we needed to do in order to collect data, build performance model, and learn the causal model based on this data. This is yet another example of causal performance model that we had. Let me skip this part. For those who are interested, actually, please look up the paper that we published at Eurosys called Reasoning About Configurable System Performance Throughout the Lens of Causality. And we have source code on GitHub and documentation. This is again the work done by Shahriar Iqbal. Is there any question so far? And how much time do we have?
I think maybe 10 minutes.
Okay. Let me talk a little bit about result, at least this part. So this is a case study that we did. This is again a system that faced a performance bug, and we wanted to find the root cause of that performance fault. And we compared with two other methods, in particular decision tree and expert advice. Our approach called unicorn, and we find out that with unicorn, we are able to find the root causes more accurately. So here, decision tree, as you see, predicted that all of these options actually are a root cause, but unicorn were able to find the true root causes, where by changing those options in the right way, we were able to gain the performance that we wanted to achieve in that scenario. And there's much more experimental result. I would leave it to you guys to go into detail of those work. And for those who are interested, essentially these paper provide a good summary of what I talk in this presentation. I wanted to also briefly mention that we have a NASA project. Is a collaborative project with CMU, a few other universities. And this is, again, related to causal AI. We wanted to show that this idea of developing a method based on causality that provide the reason and explain the reason, the root cause of performance failure, would also help in situation of autonomous systems, where essentially the approach that we took is synthesizing a plan to, for example, to adjust, to reconfigure, to adapt the system, in this case, the Europa lander, in order to, for example, recover any hardware failure when the radiation would change in the environment that it is operating. So this project, once we develop the autonomy framework based on causality, again, the causality, we used it in the part where we needed to scale up the plan synthesis, because the approach that we had for plan synthesis wouldn't scale to large state spaces. And with causal model, we were able to only focus and reduce the state spaces quite a bit. So we are able to synthesize the plan on the fly. And we evaluated the approach both in simulation as well as the physical testbed that were located at JPL. Essentially, in this scenario, we were able to build a model in simulation based on simulation data, because it's cheaper, it's faster, it's more reliable. And then once we build the model, we were able to use the model in the physical robot for decision making, for reconfiguration management on the fly when the environmental situation has changed. Okay, so I would stop here. Finally, wanted to mention that yeah, this work that I presented belong to Shahriar and a few other collaborators. And if you are interested to what we are doing, we also have a website, AIC's Lab, and I'm lucky to work with brilliant students and postdocs. And thank you for your time. I'm here to answer any questions.
Thank you very much for your very interesting talk, Pooyan. So we are going to stop the recording now, and you can ask questions. So you can either raise your hand and we unmute you, or you can just put your question to the chat.